are beginning a new section in Chapter 2, Section 4, that has to do just with the zeros of polynomials. And this is a fairly lengthy section. There's a lot of good information in here. And we're going to start it off here talking about first the relationship that zeros of a polynomial have. Now, if I have a polynomial, it's actually just called a polynomial f of x is a value. As it turns out, the zeros of this polynomial are the same as the roots or the solutions to f of x equals 0, the equation. But these match up with the x values of the x-intercepts of the graph of y equals f of x. So they're all related. All three things are related together. And since we're talking about zeros, we'll be talking about roots just as well. The zeros of a polynomial function don't always have to be nice numbers. They don't always have to be integers. Sometimes they're rational, sometimes they're irrational, and sometimes they're imaginary. So we're going to have to use some algebra skills of factoring to help us, but we do have a key theorem that helps us to locate rational zeros of a polynomial function, or rational roots of a polynomial equation. Now in this book, we refer to it as zeros. Some books call this the rational root theorem. This is the rational zero theorem. And it says if f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 all the way a sub 1 x plus a sub 0, and they have rational coefficients. All these a's are rational numbers, and the lead coefficient is not 0. And if p over q, that's the rational form there, p over q, they're integers, written in lowest terms, so you simplify the fraction, is a rational zero of f. So if I have a rational zero of f, the p and the q come from, well, p comes, it's an integral factor of the constant term a sub 0. So it's an integer that divides into this nice, neat, and evenly. And q is an integral factor of the leading coefficient, a sub n. So it's a factor of this, an integral factor. So it could be positive, it could be negative, because you could have positive, negative integers. And we look at these two guys to help us define the p's and the q's, which gives us the possible, hopefully, true rational zeros. So in the first example here, I don't want to actually find the rational zeros, and this is degree 4, so I could have as many as 4 of them. But I would like to know what my list of candidates is. So I'm going to look at first p. P could be, now remember, p is an integral factor of 8, so it could be 1 or negative 1. It could be 2 or negative 2. It could be 4 or negative 4. Or it could be 8 or negative 8. So I have 8 different possibilities. Q is an integral factor of this coefficient here, or this lead coefficient, so Q could be plus or minus 1, plus or minus 2, or plus or minus 4. So there are 8 possibilities for P. There are 6 possibilities for Q. We have to consider all the combinations of P over Q. So you have to be systematic, or you could lose something here, or maybe even double up. All right, so if I go P over Q, here, right? Let's see if I have space here. P over Q could be, it could be positive or negative 1 over positive or negative 1. Well, positive or negative 1 over positive or negative 1, whether you divide positives or divide negatives or one of each, you're going to get positive or negative 1. It could be positive or negative 2 over positive or negative 1. P over Q, remember. So that could be positive or negative 2. It could be positive or negative 4 over positive or negative 1. So that could be positive or negative 4. It could be positive or negative 8 over positive or negative 1. So that could be positive or negative 8. I could also have, I think that's every possible combination with this being Q. I could have this as my Q, my denominator, positive or negative 2. I could have positive or negative 1 over positive or negative 2, which would be positive or negative 1/2. I could have positive or negative 2 over positive or negative 2. 2 over 2 is 1. That would be positive, well, I already have that. I already have 2 over 2 is 1. I could have positive or negative 4 over positive or negative 2, which 4 over 2 is 2. I have that. So you don't need to list them twice. I could have positive or negative 8 over positive or negative 2. Positive or negative 8 over 2 is 4. I already have that, positive or negative 4. So I've got some repetitions. I'm not going to write them down twice. I have to just keep track. Now, I've done every possible combination with this is my denominator, with this is my denominator, now this guy. Positive or negative 1 over positive or negative 4 is positive or negative 1/4. Positive or negative 2 over positive or negative 4, 2 over 4 is a half, but I have that. I have positive or negative a half. Positive or negative 4 over positive or negative 4, 4 over 4 is 1, I have that, positive or negative 1. And positive or negative 8 over positive or negative 4, 8 over 4 is 2, I have that, positive or negative 2. So I had lots of repetitions, which is kind of nice. That means I don't have quite as many on my list of candidates, but I have 2, 4, 6, 8, 10, 12. I have 12 possible rational zeros. Now you say, well, you've got the list of candidates, and you know there's 4 of them. How would you actually find them? Well, I could plug these in and see, use the, oh my goodness, the remainder theorem to see which ones give me 0, and I could plug them in one at a time and go that route. It doesn't ask for that, it just wants a list of possible rational zeros. Here it is. Remember, always simplify them. Don't write down plus or minus 8 over 4, for example. Now, here I have a function with rational coefficients, polynomial function, and it wants to know the zeros. Well, the good news is my lead coefficient is 1, and my constant term is negative 2, so P could only equal plus or minus 1 or plus or minus 2, and Q could only equal plus or minus 1. So P over Q could be plus or minus 1 over plus or minus 1, which would be plus or minus 1, 1 divided by 1, or plus or minus 2 over plus or minus 1, which would be plus or minus 2 over 1, which is plus or minus 2. So I have a much smaller list. I only have 4 of them. So I'm going to do a little bit of synthetic substitution here. Let's see what happens. I have 1, negative 1, negative 4, negative 2. Now it would have been nice if I could just look at that and say, I'll factor. But that one doesn't just jump out at me at how to factor it. I mean, there's 4 terms. There might have to be some kind of grouping, but I don't see it right off. So I'm going to go this route. Now, what do you start with? Well, I just start at the beginning. I start with positive 1, then I go to negative 1. Positive 2, go to negative 2, and so on. So I will try positive 1 first. 1, 1, 0, 0, negative 4, negative 4, negative 6. Now, no good. It's not positive 1. So now, 1, negative 1, negative 4, negative 2. Now I will try negative 1. So that's a 1, that's a negative 1, that's a negative 2, that's a positive 2, that's a negative 2, that's a positive 2, that's a 0. There we go. We hit one. I have a 0 at negative 1. So I already have a 0. Here, let me write a list of negative 1. Now I could have as many as 3 because it's degree 3. Look at my depressed polynomial. I have remember, this is the constant term, the x squared term. That gives me x squared minus 2x minus 2. If I'm trying to find the other zeros that come from this, I could go to my remaining values, or since it's quadratic, it's like solving using the quadratic formula for this equation, because the roots of this equation are the zeros to the function. So this does not factor. I would have to use the quadratic formula. X equals the opposite of b. A is 1, b is negative 2, c is negative 2. The opposite of b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So I get x is equal to 2 plus or minus the square root of, that's positive 4, plus 8. Plus 8. And that's all over 2. So that's x equal 2 plus or minus the square root of 12, which simplifies, because the square root of 12 is not in simplest form for this radical. It's 4 times 3, so I can take a factor of 2 out. This would be 2 plus or minus 2 square roots of 3, simplifying my radical. Good thing we reviewed that earlier on. And then I'm going to divide 2 into both of these terms here, and I get x is equal to 1 plus or minus 2 square roots of 3 divided by 2 is the square root of 3. So those are my other 2 zeros. Notice I have one that's rational, and the other 2 are irrational. 1 plus or minus the square root of 3. So that's 1 plus the square root of 3 and 1 minus the square root of 3. And those are my zeros. If x is equal to any of those numbers and you substitute back into this function right here, you will get 0. I used the rational root to find 1 because I had a cubic I couldn't factor. If I can factor it, I'll probably go that route. But I had a cubic I couldn't factor. By finding one of the rational zeros, in fact the only rational zero, here, the depressed polynomial turned out to be quadratic. Notice it's degree 1 less than what you divide into, because you're dividing by a linear. This was degree 3, my depressed polynomial was degree 2. It's always 1 less. And so if you can get it down to a quadratic, then of course, if it doesn't factor, you can use the quadratic formula. Now let's go over to here and find the zero. Well, I've got, it says find the zeros and their multiplicities. It just doesn't have what I'm finding the zeros or the multiplicities of here. So let's put a function here. How about f of x, that would help, is equal to 2x to the 4th plus 3x to the 3rd minus 15x squared minus 32x minus 12. Not kidding around here. We have as many as 4 zeros here. Now it says, what's its multiplicity? The multiplicities have to do with repetition. See, all 3 of these zeros here were only found one time. None of them were used more than once. So they're all multiplicity 1. But over here, you know, kind of because of the directions, you got to figure that at least one of these might have multiplicity greater than 1. So here we go. P over Q. P could be, with negative 12, could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Not starting out good. Let's see. Q could be integral factors of the lead coefficient, plus or minus 1, plus or minus 2. So P over Q, let's see if I can write these in here somewhere. I'm using up all my space. P over Q could be plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, plus or minus 3 over plus or minus 1, plus or minus 4 over plus or minus 1, plus or minus 6 over plus or minus 1, plus or minus 12 over plus or minus 1. So I have all those. Now let's see what happens if you put it over 2. Plus or minus 1 over plus or minus 2 is plus or minus a half. Plus or minus 2 over plus or minus 2. 2 over 2 is 1. I have that. Plus or minus 3 over plus or minus 2, that would be plus or minus 3 halves. All right, that's not there. Plus or minus 4 over plus or minus 2, 4 over 2 is 2, I have that. 6 over 2 is 3, I have that. 12 over 2 is 6, I have that. 2, 4, 6, 8, 10, 12, 14, 16 possible zeros. Now, you can see how important synthetic division is here. And if you remember from one of my videos when I was talking about synthetic division, I had to do all these kinds of problems not being able to use synthetic division because my algebra teacher in high school decided for whatever reason he didn't want to teach us that. And that really slows you down. So you have to be careful here. Let's see if we can get started here. Let's try, we'll try 1, we'll try negative 1, work our way through. 2, 3, negative 15, negative 32, negative 12. Let's try 1. 2, 2, 5, 5, negative 10, negative 10. No, it doesn't look like it's going to work. Negative 42, negative 54. 1's no good. And if I had a little bit more space, I'd go ahead and leave that here. But because it doesn't work, and I don't have a whole lot of space left, I'll go right to negative 1. So here we go again. 2, 3, negative 15, negative 32, negative 12. I'll try negative 1. So that's 2, that's negative 2, that's 1, that's negative 1, that's negative 16, that's positive 16, that's negative 16 when I add, that's a positive 16. Well, that one's a little closer. It's 4, but I need it to be 0. So that one's no good. So let me try 2. So that's 2 and 3 and negative 15 and negative 32 and negative 12. Let's try 2, see what happens. Now, I bring the first one down, that's 4, that's 7, that's 14, that's negative 1. Negative 1 times 2 is negative 2, that's negative 34. 2, 4, 7, I hope I'm writing this down right, because if I make one mistake here, it's going to kind of scrap the whole problem here. So that's negative 34, that would be negative 68, that one's no good. Well, I hope it works pretty soon. I've already eliminated these guys, and I've eliminated positive 2. Let's try negative 2. Kind of a long process. Alright, so we go 2, 3, negative 15, negative 32, negative 12. Let's try negative 2. So 2, that'd be negative 4, that'd be negative 1, that would be positive 2, that would be negative 13, that would be 26, that would be negative 6, that would be positive, oh, thankfully, I hit one. So I have a 0 of negative 2. Now, don't go back to the original, go back to what needs to be broken down beyond this, because remember how this polynomial will factor into x minus cx plus 2 times the depressed polynomial, 2x to the third minus x squared minus 13x minus 6. Just deal with the depressed polynomial. And don't go to the next one, don't go to plus or minus 3 here. We might have a repeated factor. So I know that 1's no good, negative 1's no good, and 2's no good, but negative 2 worked once, maybe it'll work a second time. So let's see. Negative 2, so that's 2, that's negative 4, that's negative 1, that's 2, that's negative 13. I just wrote it down again. I just said don't do that, and I wrote it down again. Let's try it again. Put down the depressed polynomial. 2, negative 1, negative 13, negative 6. Oh, goodness gracious. So the 2 comes down, and that's negative 4, so that's negative 5. So that's positive 10, that's negative 3, that's positive 6, that's 0. Good thing we checked for negative 2. It's 0 twice. And look what's left. 3 terms, 2x squared minus 5x minus 3. And I want to know what the zeros are here. I want to know what the roots are of this equation. Well, I can factor that. And if I can't, I'm going to use the quadratic formula. So this would be a 2x, I think this factors, an x. Let's see, how about a minus 3 and a plus 1? So if I said both of these equal to 0, I get x equals negative 1/2, and I get x is equal to 3. Now I have 1, 2, 3, 4 zeros of a quadratic polynomial. That's it. The degree of the polynomial is going to tell me how many possible zeros I have. So I have negative 2, but it's repeated. So my zeros, because it says list the multiplicities, negative 2, multiplicity I'm going to abbreviate, 2, negative 1/2, multiplicity 1, and positive 3. Also, multiplicity 1. That one's a pretty good problem, and just think if I had left all the work done instead of erasing it as I went, I would have filled up probably a sheet of paper. Alright, the last example here is here for a reason. It says find the zeros of f of x equals x to the fourth minus x squared minus 20, the same kind of a problem that we just did. So if I look at p over q, p could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. Q could be plus or minus 1. So plus or minus all of these over plus or minus 1 will give me all of these. That's a comma there, it looks almost like a 21. So my P over Q here are all these guys. Now, I'm going to save you a little bit of effort here. I tried all of these. None of them work. So you look at it and you say, well, how am I supposed to find it if the rational root there? You got to rely on other stuff. And that is the other stuff. This guy factors like a quadratic. F of x is equal to, let's go with an x squared and an x squared. And it looks like a minus 5 and a plus 4. I said x squared minus 5 equal to 0. I mean, I know you can do some fancy square roots of 5 and stuff, but just I'm just going through the process here, and I said x squared plus 4 equal to 0. Add 5, take the square root, absolute value, I get x equals plus or minus the square root of 5. Subtract 4, take the square root of negative 4 is 2i, plus or minus is the absolute value, and you would have x equals plus or minus 2i. So it says find the zeros. My zeros are plus or minus the square root of 5, plus or minus 2i. I did check with the rational roots just to see if any of them are rational, but sometimes they're not, and you'll have to go a different avenue. Now, I'll be honest with you, I'm a little lazy. If I look at the polynomial and I can see that I can factor it, I don't go through the P over Q, the rational zero. I will start factoring. If I had this problem, I probably wouldn't have done all that. I would have just gone after it and factored it and solved it that way. But because we're going over the rational zero theorem, I wanted to make sure that I emphasized that's how you find rational zeros. If this one just didn't happen to have any of the zeros being rational.